Assalamualaikum and good day to everyone. My name is Dr. Fatimah from UiTM PASIR GUDANG. I, on behalf of S.T.E.M Innovation Team, would like to present our innovation project entitled as Wearable Stress Sensor based on multi-wall carbon nanotube composite for human monitoring. The outline of this presentation will be covered based on 5 points, which are introduction to sensor, overview wearable sensor, product description, followed by contribution to society, and the last one will be potential commercializations. In order to understand this innovation project, let's get through the basic concept of the sensor, where a sensor actually is a device measuring any changes in the environment, includes temperature, resistance, capacitance, conduction, heat transfer, and etc. Basically, a sensor can be further divided into two categories, either active and passive sensor, or analog and digital sensors. Flexible sensor is categorized as an advanced sensor where it can be used to measure any electrical changes such as resistance or capacitance based on the level of bending or deflection. As we can see in figure 2, wearable sensor can be further divided into 4 categories, which are temperature sensor, pressure sensor, integrated sensor, and the last one is strength sensor. In this project, we will be focusing on the strength sensor. So in order to know the property of sensor, it must have certain properties. A good sensor must have 3 important criteria. The first one is it must have good stretch ability. Second one, it must have very high endurance. And lastly, it must have very high sensitivity. Flexible wearable sensor can be fabricated by using different conductive elements such as metal, carbon-based, and polymer. In this innovation project, we are using carbon-based conductive elements to sense the changes of the resistance. And flexible variable sensor also can be used for different applications such as piezoresistive sensors, capacitive sensor, and also triboelectric sensor. Based on survey that I conducted in previous fabricated wearable sensor, I have outlined several problems, such as it has a very poor stretch ability, which is the elongation less than 5%. It also has low gauge factor, which is less than 100. And the last one, it has very low endurance. So in order to cater this problem, I have proposed one possible solutions in order to improvise the behavior of the wearable sensor. So I have proposed one special technique how to improvise the stretch ability and increase the endurance of the sensor. Based on the problem that I outlined before, the objectives of this project is the first one to design and fabricate the resistive strength sensor with good sensitivity. Secondly, to enhance the flexibility and endurance of the sensor. To fabricate the wearable resistive strength sensor, the first step is we have to design the dimension of the conductive layer. In order to design the conductive layer, we can use SolidWorks. After we have completed the design, we can print out the design by using 3D printers, as shown in figure 4. In this innovation project, the methodologies are divided into 3 methods. The first one is we have to design the mold of the substrate layer by using 3D printer. Secondly, we need to apply the conductive material on the sensor by using drop casing technique. The third one is we have to do a further characterization by identify the conductivity and the physical properties of the sensor, such as flexibility and endurance. Actually, based on the second method, we try to improvise the properties of the material, such as the flexibility and endurance, by using the special technique. In the first methodology, we need to design and print out the mold of the substrate layer by using 3D printer, as shown in the figure. Then we pour the special liquid sample that we have proposed into the mold. After the mold gets cured, we can extract the sample from the mold, as shown in the figure. In second methodologies, we are applying the conductive material on the sensor. So it has 4 steps. The first step, we have to prepare the substrate layer in the mold case. The second one, we need to prepare the treatment solution. Okay. This treatment solution is a very special treatment because it can enhance the flexibility and conductivity of the sensor. In step number 3, we are preparing the conductive solution before we apply it on the sensor. And step number 4, we are preparing the final prototype by embedded the electrodes on the sensor. After we have fabricated the strain sensor, the next step is we need to do further testing in order to ensure the performance of the sensor. So we have conducted 2 different tests. The first step is we conduct the conductivity test, which is we want to test the sensitivity of the sensor. Secondly, we conduct the stretch ability and endurance test in order to check the endurance and the flexibility of the sensor. The outcome of the testing, we're able to know the conductivity and also the behavior of the sensor. Okay, for the first test, we want to conduct the conductivity. So the output of this test can be summarized in figure 5. The result shown that the conductivity of the sensor has been improvised significantly, and this result represents that the response and sensitivity of the sensor has been improvised. For the second test, we are testing on its flexibility. Okay, the result from the testing can be summarized in figure 6. So the result on the left shown for before treatment, while the result on the right shown after treatments. Based on this result, we found out that the surface treatment that we have conducted have improved the endurance and flexibility, where we can see before the treatment, the strength level can achieve up to 250%. But after we do the surface treatment, the strength level can achieve more than 3000. Based on the result that I have shown earlier, the fabricated strain sensor has very good conductivity and high endurance level. And another good thing is about this product is it's very compatible with human skin. The benefit of this product to society, the first one, it can help in rehabilitation monitoring device on human. Secondly, we can further implement it for various applications like construction and instrumentation. Lastly, for the potential commercializations, this product can be extended as a rehabilitation kit sensor with IoT system. Other than that, it also can be used for robot hand movement and also can be extended for various applications such as construction and instrument applications.